Okay, let's see how this goes. I'm going to be doing an example, HEC-RAS example using Civil 3D, basically create the surface, and then exporting that surface into HEC-RAS, running a simulation of course, and then exporting the results from that via QGIS all the way back to Civil 3D so that you can use the results on a drawing of some sort. We will be assuming that we've got some sort of surface input data that might be from any survey. I'll get back to that later, and then just a road to complete the picture for you guys. Just as a short disclaimer, I am no expert in any of the software packages that we will be discussing. I do not use them every single day. I do not use or know the ins and outs of every single package. I don't know all the settings. Obviously I cannot take any responsibility in what you do and what results you get. It is what it is. I basically work on trial and error to get stuff working. See what works, see what doesn't work. What works for me might not work for you. I do not discuss any of the packages in detail. There is a hell of a lot more that one can do with it, and basically do to improve your results that you might get at the end of the day. To start off, we will be starting a new Civil 3D drawing. Blank, obviously, as you guys can see. Firstly, whenever this thing starts up and it is ready to use, we will just make sure that the units are set to meters. That's just a general standard that normally works very well. Since we've got a project and is obviously located somewhere on Earth, we will have to georeference the drawing. That can be done by typing in the following command. In Civil 3D, of course, that would be ADSESE set CRD system. So basically, I don't know what it stands for, but anyway, we are going to set the coordinate system. We can select a coordinate system from the nice little long list that we've got. Currently, we will be working in South Africa. We will be using the Hartebeespoort LO29 system, and we can set that. All of this will just be normal, plain and standard. As you guys can see, that is done. Earlier I spoke about the input data that we will be using. One of those files obviously is a road, so we can add that road into this specific drawing. It'll obviously be referenced, located in the correct position on Earth. So let's just quickly add that example, the road. Once that is done, scale is fine, specify on screen no, let's just put that in 0, 0. Middle mouse button, so we've got a road somewhere in 3D space. As you can see, it is relatively 3D, it's not a perfect model, but hey, this is what we got from somebody else. Just to confirm that this is actually in the correct position, we will be using satellite imagery from the Bing server just to check that it is actually in the correct place. The way you can check that is by typing in Geo Map, and then we would like the aerial one. For this aerial map to work, you will have to be logged in, and you will have to click allow online data to be used. Once you've clicked OK, basically turned on the aerial map data, you'll see it freezes for a few seconds since it has to download the data first. It is going to take a while, and this is happening in real time. I'm not going to pause it. Okay, cool, there you can see it is responding again, but I don't see anything. Wait, I see something up there. Yes, we've got an image. As you guys can see, it is not in the correct, well, it's in the correct location according to AutoCAD. Since our road is over here but the image is all the way up there, it basically means that the survey was done in a different hemisphere, because Civil 3D is normally working in the northern hemisphere because it was programmed by Americans. Anyway, so what we need to do is we need to rotate our XREF by 180 degrees so that it falls within the correct position. That's just plane from 0, 0 where we inserted it, 150 degrees, and now, as you guys can see, it is on the image at least. And if we zoom in on this, this is obviously the XREF is the plan for the new road that they will be constructing, and as you guys can see, it relatively lines up with the image that we've got. Now, to include a Bing image that is not dynamic and updates while we zoom around and pan around and so forth, we can include a Geo image, Geo Map Image, by selecting a little square, and that will be saved over there. So then we can turn off this map by typing Geo Map, and we turn this thing off. As you guys can see, this one remains here, but as you can see, it is absolutely horrible, so we can change the quality to very fine. It reloads it and it looks okay-ish. Okay, so now we know that we are actually in the correct location on Earth, which is a very good thing to know. Let's just quickly do a little bit of cleaning up with the layers. We will have an XREF layer, and then let's create an image layer as well, so that we can put all of this nonsense on layers that does not bother us. Obviously, as you guys can see, everything is brand spanking new. Okay, so this image we want on layer image. This XREF we want on XREF. Then we can turn those layers off. Just turn the XREF layer off like a normal person. And once again, we've got absolutely nothing in front of us, which is okay-ish. Let's just save our project for now so that we know that we don't mess it up. Let's call it a Civil 3D drawing. Okay, now we need to create some sort of surface that we will be using in HEC-RAS. For that, what I'm going to do is I'm going to open the surface input data as a separate drawing. I do not want to import it as an XREF. As you guys can see, on this specific drawing we've got a bunch of points. That was obviously some guys did a survey, and I already created a few break lines defining the new road geometry along the road. So that will help us to define the surface more properly, and then I've got a boundary for the surface as well. All of this I'm just going to select it by pressing Ctrl A, Ctrl Shift Copy. I'm going to copy it with base point 0, 0, 0. All of this we will then go back to this drawing, Ctrl View, insert it at 0, 0, 0. As you guys can see, it once again popped in over here. Let's just make sure that it is in the correct position. Going to the image layer, turning that on, and yeah, that looks roughly okay. Let's just turn that image layer off again. Now we need to create a new surface. There's obviously a lot of different ways to create surfaces. You guys will see that there is multiple definitions, but let's start from the beginning. We create a surface, we can give it a name. Let's call it NGL. Then we go to surfaces, NGL, definition. The definition obviously defines what we've got in this surface. We can have boundaries, break lines, contours, other files, point files. So this actually allows you to import point files as text files without bringing them into the drawing by themselves, like all of these points that were drawn. That we're not going to do at this stage. Point groups and so forth. Okay, for now let's go at drawing objects. We're going to add drawing objects to this surface. Let's just use the points, so it's points, and then we select all of the points. It'll filter out all of the polylines and so forth that we don't need. We do that. As you guys can see, we've got some surface with Contras displaying at this stage. I'll talk more about that and the displaying of the surface in a while. Now we need to add some of these lines as well, all of my break line / lines. So let's just add more drawing objects, because it is drawing objects for that matter. Lines, let's call it break lines. Break lines, we select it. I'm going to select it in such a manner that I do not select the boundary line. Selected. This little menu pops up. This normally happens when there's errors on the surface. This mostly happens in locations where your entities overlap. Let's say, for instance, you've got two lines on two different elevations and they cross. This will obviously cause issues when the surface is generated. Mostly it's not that big a deal, but you can zoom to the individual problematic areas and correct them if you'd like to. At this stage I'm not going to worry about it because I know it works. After we've added the drawing objects, we are not going to add more drawing objects, but we are going to add break lines, like proper break lines. That can be done by adding the break lines like so. Weeding factors, distance, mid-coordinate distance. I normally leave all of that stuff as standard. Type, standard should be okay. And once again we select the same lines we just imported. But this time it will be used as break lines, not as drawing objects that was used to create the surface. Adding that, as you can see, we have a lot more errors, but once again I don't think that should be an issue. And let's add a boundary to the surface just to clean it off. It is an outer boundary, mid-coordinate distance, non-destructive break line. I don't know what that means, but okay. We add the break line like so, and voila, we've got a break line, a boundary line, and voila, we've got a nice boundaried surface. Okay, let's talk about the displaying of the generated surface. As you guys can see there, we can see contour lines, but they're very far apart and they look a little bit horrible. So we can, let's just quickly turn off all of the input data. You guys will see that if I turn this off, the surface will generate not errors, but it will show that there has been changes to the input geometry. Don't worry about it. You can set it to manually recreate the surface or automatically. I think mine is set to manually doing it, basically rebuild it. I'm not going to do that now. Anyway, to change the display style of the surface, you right click on the surface name, edit surface style. Then we've got a bunch of little options that we can do. Let's first go to display. In plan view, model and section. We are currently in plan view. We can see the border, major contours and minor contours. For time being, let's just turn that off and let's turn on the triangles. And voila, we've got the triangles. Let's change this once again to contours, but the contours, as we saw the previous time, is absolutely horrible. So let's improve the display style of that. So we go to contours, contour ranges. I'm not going to change the contour range. The contour range seems fine. Contour smoothing, that might help, but before we do that, let's change the contour interval. Currently it's set to 2 meters and 10 meters being the major and minor contours. Let's change that to 5, and let's say that to 1. No man, 5. Listen to me. Okay, perfect. Apply that, and now we can see more contours, but it still looks horrible. Let's change that so that we can see slightly more. Contour interval, let's make it 0.5 meters, 2.5, that sounds about right. So now we've got a lot of contours, jaggedy edges everywhere, and let's smooth that out slightly. That would be contour smoothing. Currently it is set to false. Let's make that true, and how smooth do we want it? It's contour smoothing. Let's make it very smooth. That's close to very, and it looks slightly smoother. Still not great, but hey, that is the survey that we've got. And obviously you guys can change all of the colors and so forth, as you guys saw. I think changing it over here, but I'm not going to change that now. I'm happy with the contours as is at this stage. As soon as we go to rotate this model, you'll see that it changes to the other display style. This display style is obviously the 3D one, or the model one, which we can change by doing this, and then we can see the contours again as we did in the plan view. Sometimes, depending on your surface, you would like to see the contours or triangles. It all depends on the use case. While we are in this specific view, we can quickly check to see the boundary of the road, just to see that it actually looks like we expected. As you can see, the wall starts right about there, and it curves around like that. Everything looks relatively okay, and as you can see, the wall goes shallower, or shallower all the way to there. So we're happy with that. A nice little trick that I saw the other day was if we change this display style not to contours but to triangles, and then we can go to triangles and we can exaggerate this specific style. Exaggerate elevation, let's make that a 3. Apply that. Let's just go back to display and we turn this border off so that we don't see the border. Okay, this layer is still active. Let's just turn that thing off. Now it is the same triangles, but they are exaggerated 3 times in elevation. That's why it is a little bit higher than we normally expected, and well, it's exaggerated. That's basically it. But that way you can sort of get an idea of the water course, where the water will flow. Just to clarify for you guys, the water will be flowing from this side that way through the model. And that's about it. Let's just quickly change all of this back to a more usable view. Use surface elevation, that's what we want. We're fine with the triangles in the model view. Nah, I like the contours more. Let's change it back. And I like to see the border as well. So that's that. We don't want to see all of any of those. Yeah, that's about it. Apply. Okay. Go back to the top view, plan view, and there we have it. Next, with this being a HEC-RAS model, we will obviously have to be allocating or assigning manning values to the different areas of our model. Just to give us an idea, let's turn this background image back on. The manning value in, let's say, the rough tree, large tree area, and then of course smoother areas along the the river, well, on the banks, river banks, and then in the channel itself. The way you can do that is obviously by making use of the background image. This background image just aids in the actual drawing of the boundaries. There's multiple ways of going about this. You can either draw physical polylines, basically using normal polylines, 2D polylines, to create the boundaries themselves, or you can use polygons as well. Let's just quickly create one so that you guys can roughly see what I mean by this. Let's say I know the extent of our river and surface that we've got is only bound by this boundary, but let's draw in another thing, because it doesn't have to be linked to the surface itself. So let's quickly just follow it roughly like that. I'm not gonna do it completely at this stage because it is rather time consuming. So voila, we've got a little area. Let's just create, as an example, the polygons as well. In my previous little segment I used polylines. Let's just create polygons as well. Polygons is basically similar type of thing. It's a polyline that you draw as a boundary of some sort, but the only difference is that I could, after you've drawn it, it automatically hatches it for you, as you can see over there. And if we go to this view where we can see the properties, let's bring this into frame, you can see that it is an polygon. I honestly don't know what's the difference between that and a normal polyline, which is basically closed, because it's very similar. Once you have, just undo that, once you've created all of your boundaries, you should allocate them to specific layers. In this case, we will be allocating them to Manning map layers. So we can just open the layer tab. Where is that? All layers, yes. We can create the different layers that we need, basically defining which Manning value we will be allocating to that specific zone. Let's just go and create one for now. Manning, let's call it semi row. That's a decent one, and let's change the color, not white, just for quickness, and we change that to layer Manning. Ta-da! Okay, cool. So we've got that little one. I'm going to copy and paste the Manning regions that I've created before this video, just to speed up the process, and I'll show you the end product. And magic, we've got our Manning regions drawn in. Just to give you an idea of what's going on here, I've got this Manning, this green Manning polygon. It would be trees and dense vegetation, as you can see over there, and then we've got not so smooth banks. Then we've got the red one would be smooth banks, and then the natural defined stream, and the road will have gabions on the side, so we would like to allocate a specific Manning value to the gabions along the road, so we've isolated those areas and drawn in a little Manning zone for that as well. After we've done this, we need to start exporting the specific maps that we've got. Firstly, we will have to export the surface and then the different Manning regions. Once we've done that, we can import that into HEC-RAS. For now, let's just start by exporting the surface. That's done by going to your tool space, surfaces, right clicking on the specific surface, and then we can say export to DEM. This brings up this little window right there. As you can see, that's the surface name, a description. It's already coordinated. We can give this specific DEM file a name, Let's call that it's an NGL dim, seems roundabout fine. Let's do that, save that. It would be to 21 grid spacing. That's the grid size that we will be using for the generated surface. I suggest keeping that relatively small, just to improve accuracy. You don't want to make your surface coarse, unnecessarily coarse for the use in HEC-RAS. Average elevations would be fine in this case, and then we click no, does not support the selected coordinate system, blah 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 blah. Okay, let's change this then. That should not be the DEM, it should be a GEOTIFF. That makes sense, because HEC-RAS uses TIFF files anyway. Let's do that, and now it's busy exporting surface using mean elevation. So that would be the mean elevation within the grid size that we defined for the surface. So that's also a reason why you should make the grid size relatively small, to increase the accuracy, so that you don't get unnecessary bumps in the surface. As you can see, that has been completed. Now we need to export the Manning map. I specifically positioned my Manning zones in a different location below the surface, just for easy selection during the creation process. Okay, just to show you guys that we've got the Manning layers specifically defined. Once again, before we export it, we've got the smooth banks, we've got the trees and dense vegetation, not so smooth banks, and then the mainstream channel, and then the pink stuff is the Gabion wall. Okay, to export this, you firstly select all of it, you type in map export. Map export, we will be exporting it as a shapefile. There's a bunch of different options that we can do, but shapefile is the one that we want. Let's give this a Manning map layer, and then we say OK. Now it comes to the selection of the stuff. If you didn't select it before we typed in the command, you can go select manually, and then you can click on that little thing right there, and then you can select the actual objects. As you can see, currently it is filtering out all of the objects selected. That's because the object types that we want to export should be polygons. Now none of it's filtered out. Then when we go to data, we should select the attributes which we would like in the exported shapefile. Since we specifically put the boundaries on different layers and named it correctly, we wanted to organize it via the layer. And as you can see, that's the source that we want to add. And then if we go to options, treat closed polylines as polygons. That basically does exactly what it says. This all seems fine, and then we can say OK. As you can see, 22 objects selected, exported in 0 seconds. So that actually worked. Now we will be heading over to HEC-RAS and set up a model there to start. Moving over to HEC-RAS, let's just quickly clean up all of the drawings that we are not currently using. The Manning map, and then of course the Civil 3D drawing that we created. Let's quickly save that so we don't lose it by mistake. So we minimize this, we open HEC-RAS, we will be creating a new project. This new project will be saved on my desktop, because that's how I'm gonna do it. HEC-RAS example, let's call it road. Yeah, that's okay, I don't really care about the name, road. Start a new project and find a road as it that would be SI units. I'm happy with that. We say OK. Now, to start off, let's open HEC-RAS Mapper, because in HEC-RAS Mapper you can import the terrain that we exported. The terrain meaning the GEOTIFF file that we exported in Civil 3D. So that's that NGL, the TIFF file. So here we go. Tools, new terrain. It's recommended that. Would you like to set it now? No, we do not want to set it now. You can do it if you do not use Civil 3D to assign the georeferencing portion of this model, but in this case, since we've got a georeference TIFF file, we do not want to assign it now because we will do it when we import this TIFF file now. So there, once again, there they give you the warning over there, but that's not our problem. HEC-RAS example, the NGL. Open. The RAS model currently does not have a spatial. It has a projection associated to it. Let's do that. Yes, that's fine. Cell size 1 meter. That's the size that we assigned in Civil 3D. So now we create it. Hopefully you don't get any errors, and then voila, we've got a terrain. Now to zoom to it, let's just close that and then reopen this. Nope. Zoom to layer. It's not working great. Ha, no, we've got it. Lies. Lies. Why is this all green? That shouldn't be. Let's quickly look at the layer properties. That number of values not 1. Why is that 1? Create. Apply. That's better. As you guys can see, we've got a surface and it is not that well defined, but that's because of the survey. You can also go and manually define that surface a lot better in Civil 3D, but for the purpose of this video we're going to accept it as it is. Okay, so we've imported and generated the terrain. Now we would like to add the land cover layer. That's basically the Manning map that we also exported. That's a new land cover. We would like to import it, and that is the, just change this to something more usable. We've got the Manning map. We click on this shapefile because that's what we would like to import. As you can see, it's a TIFF, FLT, or a shapefile. We go shapefile. Manning map. I can't believe that. Lies. Lies. Also not. Okay, and a few hours later I think I've pinpointed the problem with the import of the Manning maps. I was checking an example file that I used previously to export the stuff from, and it works if I export it from this drawing, but it doesn't work if I export it from this one. And the reason is because of the coordinate system that we set. For some reason, Civil 3D does not like the RTBS hook allo 29 system. Let me just quickly see, because let me show you. The one that we've got in this drawing, the one that actually works, is that allo 29 South Africa Survey Grid WGS 84 datum. That one works. And this one we have, that would be set coordinate system RTBS allo 29. So this doesn't work. So let's see if I change it, if it actually works. So that would be South Africa. So the RTBS hook one does not work. allo 29 survey grid, this one. You still use the WGS 84, so that one and that one would be the same thing now. So let's change it to that. Select it. Say OK. As you can see, it changed it slightly. I'm pretty sure that we will actually see that this road lines up slightly better with the image now, but anyway, let's just ignore that for now. And let's try and export this thing again. The amount of frustration that went into this. Anyway. Map export, Manning, map, or let's call it 76, 67. Then we've got polygons, that data, do the exact same thing we did previously, but this time it'll actually import on the other side. Treat that as closed, so we've set all of those, that select manually. We've got 17 objects selected. The polyline should work without any issues. Okay, cool, so we've exported that. Then we go back to RAS mapper. While I was busy trying to figure out what I did, the only thing I actually did was I went to HEC-RAS and I created just a basic clean geometry with a 2D area, but as you can see it was rubbish. Let's just clean this out so you guys can see that it is actually a clean HEC-RAS thing. As you can see, once again we've got just that and just this. Just close that, let's open that up again, then, well, nope, remove that. Okay, cool, so we've got absolutely nothing. That's basically where we left off the previous time. Now we go and we create a new land cover layer. Same thing we tried the previous time, but this time it'll work. As you guys can see, that's the one we created, and we open, and voila, we've got the different layers. Now we can assign specific Manning values to the specific areas. For now I'm just going to hoy in a bunch of values. That's not so smooth. Let's make that around about 5. Smooth bang 0.03 should be fine. 0.6 and 0.12. That's around about fine. Let's make this nice and small, similar to the surface, the natural ground line surface that we created. Creating that, close, that happened without any issues. Now we can see there's a map layer. Let's turn that on, and then you will be able to see the actual layer on top of your terrain there. We can actually look at the values. As you can see, we've got, if you click on the land cover layer, or any layer for that matter, you can see the data assigned to that layer. So in this case we've got that is Manning trees dense veg with the Manning value equal to that. That's different, and different. So that's kind of cool. Just to give you an idea, we can actually check the terrain to some extent. If we do a similar thing, we can go to a specific known portion on this terrain, see what the elevation is, 1586.12, and then we can go back to Civil 3D and check if that is within the same elevation. Okay, cool. So that's an initial startup for the importing of the terrain, and then a land cover that will be used for all of the Manning values. Okay, since we've set up all of the geometry, well, most of the geometry by importing the terrains and the land cover layers, we can go back to the normal HEC-RAS window and actually start with setting up the geometry file itself. For this example, we are only going to work with one 2D area. You guys should know that you can connect 1D and 2D areas together, but I'm not going to cover this in this example. So basically how we start off with this is we click on that little thing, and then we go and trace the area that we want in our 2D area. I'm going to do this very rough at this stage. You can obviously spend a lot of time on this, tracing this. If you press and hold shift, and then as you guys can see the cursor change to a little hand, and then if you click and drag, you can drag the map around. That helps with navigating because zooming in and out with the HEC-RAS 5 is absolutely horrible. They should honestly work on that. But anyway, let's just trace this and then see what we get in the end. What you guys should also avoid is, because it is going to cause problems later down the line, is if you are not careful and you specifically click or create this 2D area, that it falls outside your land or your terrain file. So I'm going to purposefully create an error now, and then we will come back and correct this at a later stage, just to help with debugging along the way. As you can see there, I specifically missed it, so we will get errors when we create that or try to run the file. Yes, come on. Okay, so we do this, that, and okay, not gonna put in too much effort now. You guys will notice when I run this file that we actually have too little survey for this model, but that's part of the problem. So we did request more survey to be done. Anyway, let's give this 2D area a name. Let's just call it river. Okay, my display style is set that it doesn't display a lot of stuff, but okay, anyway, let's just do that. So now, to create the actual mesh of the 2D area, you click on the 2D area that it selects it, and then edit 2D flow area. You'll present it with this value, or this little window. There you can select your 2D areas. You can convert this 2D area into a storage area. I'm not going to do that. We want to work with that one. The default manning value is basically what you assign, that if your land cover layer does not cover that specific area of your 2D area, it will default back to this value. I think 0.06 is fine in that case. I'm not going to change those stuff. This little command right here, over here you can specify the computation point spacing. Basically, how far apart should the centers of the mesh or the elements be for this specific map. This does not have to be very big, and it doesn't have to be very small either. It's just the way HEC-RAS handles it. I'll explain a little bit more about this later, but for now let's make it nice and small, 5 meters spacing. This will definitely work with the SI unit set to the to your project, and we are working in meters, so that is 5 meters and 5 meters. You click on generate, then you'll see the mesh contains 3,159 cells. That is a lot, but so what, we've got powerful PCs, so it shouldn't take too long to compute. You press OK, and then you see that it generated the points or the mesh. Yours will most likely look slightly different. Yours will look, you can change the view style in view options, and yours will most likely be set to look like that. But as you guys can see, then you can't see what's going on below it. I personally like the other view slightly more, but for editing and refining the mesh, this will help. So let's close that. As you can see, now we have to check the mesh. The way we would like to avoid sharp edges in the mesh, that's normally along the edges of the geometry, but in this case it doesn't look too bad. But let's add a few points just for the sake of it. Edit, add points. Let's turn this geometry off so that we don't see it, because it is irritating me. View options. Can you change it over here? No, you cannot change it over here. You change it right here. There you can turn on the land cover layer if you want to, or you can say plotted terrain. Let's turn that off. Okay, so now we can do this, add points, and then you literally just go about your mesh and clicking wherever you want more nodes. You can go all around this boundary. You will notice that even though HEC-RAS generates a mesh by itself, you will sometimes notice that it generates well, problematic areas. Those problematic areas will be highlighted in that the cell centers, these little black dots, will not be black, they will actually be red. So it will be clear where you've got a problem. And then you can manually go and either move the points or delete them or add more. It's part of the fun, basically just refining the mesh to some extent. You can obviously go and add a lot more points, not just on the boundaries, but everywhere where you would like the mesh to be slightly finer, especially if you want specific information from a portion of the map. So for instance, this is a narrow area, so we're expecting a lot more concentrated flow to go past this area. So we might want a finer mesh in this location. So then we can literally go and add more cells in here. The way HEC-RAS 2D or HEC-RAS 5 handles the 2D area is all of these cells has got a bunch of faces. That's basically the boundary lines as you guys can see it. So like that boundary there, and that boundary there, and that boundary there. All of those boundaries are actually treated as cross sections. So each cell contains a number of cross sections, and I think the maximum amount of faces it can have is 8, if I remember correctly. So this is actually pushing it close to the limit, because that's almost like 6 there, 7 there, so that's close to 8 anyway. But if it's got issues with that, it will inform you when you run the program or try to run the analysis. Okay, I'm assuming that's an okay adjustment for now, because I'm probably going to have to redo this anyway. So we've got that. Edit. You can also remove points. Let's remove a few just to show you that it actually works. I didn't like that one, or no, then it creates that and I don't like that. Ooh, nope. Let's add a point again. We like that one, but we want to move it. So we want to move it from there to there, and as you guys can see, the mesh dynamically updates as you move stuff around. That's a very big one there, I don't like that, so let's add a point over there. What you can do and what should be known, the Manning, the land cover layer is applicable to where this specific node is located. So in other words, this node or that cell, for instance, will use this land cover area as its Manning value inside it. If I move it to that one, now it's going to use that. So it doesn't matter where the cross section is taken, it is all dependent on where that node lies or falls on your land cover layer. So if we move it there, it will be applicable to this land cover region. If we move it there, it's going to be the pink one. That is quite significant, because for instance on this edge, this blue layer over there, that would be adjacent to the retaining wall or the gabion wall that we've got there, and we would like to have that set of cells a slightly lower manning value, because the water will be able to flow faster there because it's a smoother surface. So what one actually would like to do, if you put a lot of effort into your mesh, you can add a bunch of points or move them that it falls nicely within that area. Then you know that all of those cells will use that specified manning value. That gives us the idea of that, and then we've got the mesh refined for now, and that's roughly how you can see that. Now next we will add basically the entry and exit locations of well, basically where the water will go into the 2D area and out of it. So we can 2D area boundary control links. That's basically done. You click on that thing, and where we want it from there to roughly there. You draw it on the outside, and you press, well, double click, and then you give it a name. That would be the entry side. And then it goes and wraps the entry condition around that, or the closest 2D area for that specific one. If we go to edit, we can move that, because let's say it was too long or too short, you can move it slightly in, and as you can see, since I double click there, I've got more than one node, so let's move it like that. And then nope, we don't want that one node, so we can remove that point, and now it's tidied up. Let's go back to this, because we've already done the entry. Now let's do the exit. The exit is there. Okay, so then if we click that, then it diverts back to that. As you can see, since we changed it, it shortened the entry zone, or basically the gate, if you want to call it that, and then there we've got the exit one. So that is basically all of the setup we need in the geometric data editor to set up the geometry. So let's save this now as a geometry file, and that's it for this. Okay, next we will be assigning the boundary conditions for the simulation. That's done in this little window. We can only do the unsteady flow with 2D areas, but it works on a hydrograph. So we will be assigning a constant flow through it, so that it will act as if it is a steady state problem. At the exit, we will assign a normal depth, friction slope like normal 1D HEC-RAS. In our case it's 0.067. Then for the entry we use a flow hydrograph. Okay, as you guys can see here, we've got, you can get a path, we can get a simulation time. That's normally the easiest way. We are going to, let's open Excel for this, and let's put in, assign that the hydrograph works in hours, and then we can just quickly open that. Let's call it 24 hours, so it's 1, 2, 3, and then we go all the way to 24, and let's put around about, let's make it 150 cubes. So we've got 150 cubes over a time frame of 23 hours in total, and we would like the minimum flow. We set a minimum flow of 0.05. That's not going to influence us at this stage. We don't want a multiplier, so let's make that 1. The energy grade, let's make that the same as the boundary condition. Monitor the diagram for adjustments to computational step. I don't know what this means. Anyway, let's leave it like that. That's all that's needed there, so we can close that or just minimize that. So we've basically assigned that. Initial conditions, you can use a restart file. That is mostly beneficial, especially because 2D areas cannot start dry. You will notice when we run the analysis for the first time, the first few iterations will produce errors, or at least some sort of error, and then it'll smooth out later on, especially when it is basically at steady state conditions. So that's done. We don't want to set anything else here, so we can save the unsteady flow. Unsteady. Okay, and we can close that. Now it is time to see if we can run it. We might as well. So, for 2D analysis, we normally change the you can change the calculation options and tolerances in this menu. 2D flow, we do not use the fusion wave. Full momentum wave is more lenient when you get sharp or abrupt flow changes. Full momentum, well, in all of the examples I did before this one, I got the most reliable or smooth answers without weird anomalies happening. So use the full momentum wave. That's what I suggest. Obviously you can change all of the other tolerances as well. We are happy with this as is, I think. Can't remember of anything that we need to change. So now we've got just one geometry, we've got one flow. We want that, yes, no, we don't want to include that. Let's just pick those even though we haven't used it. Today is fine, or that day is fine. Starting time 000, ending time it was 23 hours. Ending date, that'll be the same date because it's still within that day. Computation interval, let's make that slightly longer for now. This will produce errors, but I want you guys to see what happens if it is not that small or that frequent. 30 minutes. Mapping output interval is an hour. Let's keep that the same as the computation. Then we know we're looking at everything that's computed. Hydrograph interval, we got that, and a detailed output interval. I don't know if I can make that the same. Let's see. That. Okay. Level output. I don't know what computation level output is going to work. Nope. And let's say it's a mixed flow regime, then it normally jumps between the two. File. Save plan as plan 1. Plan 1. Okay. Then we say compute. Then we get our first error message. The interval for detailed output is less than the hydrograph output interval. So, since that's a problem, let's make that the same. Compute. Whoop. Once again, it got past the point with the hydrograph not being the same or bigger detailed output interval, but we got other stuff. Data for 2D area is missing. Checking the association and 2D mesh problems. So we've got issues. Line that, I line that as well. So that will be because of, I don't know, let's check the 2D mesh. So save that, do that. 2D mesh, like we saw, we didn't get any red node, so there's no specific mesh element that is causing the problem, but we know about this issue that we caused where the 2D area actually goes outside the terrain. So let's modify that and see if that solves the problem. So we would like to do this: edit, move points, or no, let's add one. Edit, add a point on that, but we're going to move that point now, and we move it in. And then, as you guys can see, we've got a bunch of nodes outside the boundary. Let's remove them. So that one, that one, that one. That should do it. That's it. As soon as it was fixed, you could see the mesh being generated again. So let's save this and run the analysis again to see if it computes. And we're going. And as you guys can see, we got an error with the program RAS unsteady, that with that specific exit code. I don't know exactly what that means, so we'll have to figure it out. Let's try and find it. Okay, normally computation errors like that doesn't refer to specific cells or the geometry is caused by two things. It is either the computation interval or computation interval, and it might be linked to your geometry, but it's mostly the cell size. So let's fiddle around with the computation interval and see if that solves the problem. Like I said in an earlier segment, the 30 minutes is rather long, so let's make this 1 minute and see if this works. Let's change the mapping output interval as well. This will obviously significantly increase the computation time, but let's see. Once again, lots of errors in the beginning, a hell of a lot, and the error itself was actually rather significant. And we get another error, so that did not work. Let's try something else. Let's edit the mesh. That obviously all of the customization, the extra nodes, extra mesh that we placed is gonna get removed now. Let's make this nice and big. Make it bigger. 15. Yes, I know that. 331 compared to 3000. That's a lot less dense. Let's save that. Let's compute this again. See if we get the same error. Errors are a lot smaller, but we still get, it still falls outside the tolerance. As you guys can see, it's limited to specific cells. We can always go and refine the mesh around those areas, and that will help limit the amount of errors that we get. Just to give you an idea, that error is in meters, so having a 0.003 error, for instance, in meters, so a 3.3 mil error is not that significant, so that could be acceptable. But for instance, this one over here is almost close to 0.25, so that's 23 mil. That might be out of your spec, so we tend to try to keep the simulation to produce no errors. But let's see where it happens. So we are looking at cell 194184. So let's look at that. So you click on that, find cell 194. Okay, so it doesn't like that little portion. Let's add a bunch of points in the vicinity, basically refining the mesh. I'm doing it very, very crude now, so it is definitely not ideal, and I don't like this big mesh, but it shouldn't should still actually produce relatively accurate answers. The mesh really doesn't have to be that small like we did initially. Saving the geometry. Now we can compute it again. Still a bunch of errors. Error sizes similar to what we experienced the first time around. Okay, I'm not gonna spend too much time trying to minimize these errors now, because I know this mesh is slightly too big. But let's look at the results that we got from that analysis. So we've got, going back to RAS mapper, we've got results, result plan 1. The geometry, you can turn that on, doesn't show anything. Pew pew pew. Anyway, so let's do that. We've got velocity. This is showing the max velocity. As you guys can see there, we can do this whole slider thing, and that changes it slightly. As you guys can see, the actual display of that is a little bit limited. There you can see a scaling, and obviously the range is completely out. So let's change that so that it looks better. Layer properties, that the max velocity looks around about 4.5. Let's make it 6 meters. 7 bands is fine. You generate it, it automatically updates that for you, and voila, we've got a better representation of the flow velocities. We can change this even further so that you've got Contras, and let's say at 0.5. So now it plots nice little flow velocity Contras, if you want to call it that, and you can directly see where the flow is taking place. As you can see here, if I run the slider along, it remains roughly steady, assuming that it is steady flow, or we can assume that it is steady flow in that vicinity because it doesn't really change. In the beginning, where the water actually runs down, we can actually run this. As you can see, it freaks out a little bit because it's still getting that steady state, and because of the computation time and the size of the mesh, a lot of errors can cause that. But like I said, the rest of the analysis is relatively stable, so we can sort of accept that, but that's about it. So we've got results. We can obviously look at the water depth as well. Once again, the scale is a little bit out, so we can change that to be more representative. And let's make that just a little difficult to judge the depth now, but let's make it 5 meters. That looks around about okay. And then we can even plot a few flow lines on this as well. We do that, and we look at the and then you can see the water flowing on the banks. You can see that it flows a little bit slower, and this will obviously correspond to the flow velocities that we're getting. Let's just turn that off. As you can see, faster over there, and then slower around the banks. Back to that, and then applying the flow lines again, similar to what we see. Okay, but let's try to improve on the amount of errors that we were getting, and see if we can smooth that out to some extent. Let's turn this on, let's keep that on, turn that off, go back to the HEC-RAS. Let's change this. I don't like this extremely big, well, not extremely big, but let's relatively big. Let's make it 7.5 meters, 7.5. Yes, so we're replacing 300 and something with 1,372 cells. That's a little bit better. At this stage we don't have any problematic nodes highlighted with the red cell center, so let's just assume that is okay for now. Save that, close that. Let's go back here and let's change this 1 minute computation interval to, let's make it 5 seconds. 5 seconds. Letting that run. Still getting a lot of errors. And now, after that's about time 6 minutes, I think. Yes, 6 minutes, 25 seconds. We are no longer getting any more errors in the results. So that's a good sign already. And that is most likely mainly due to the computation time being a hell of a lot smaller, so every 10 seconds instead of every minute. And then of course the mesh itself is also slightly more defined, giving us more results to iterate between or compute between, which is also a good thing. Okay, we are nearing the end of the analysis now. Still no more errors generated. Yep, it's taking a while, but not that long time. Almost 23 hours now. Okay, almost 20 hours. Okay, as we can see, it's done computing now. Let's go look at the results and see if it looks a little bit smoother. Okay, let's make this full screen. As you guys can see, the boundaries of the water level is already a little bit better defined. That could be because of the finer mesh. We don't get the jumping of water level in this vicinity where we did get it in the previous set of results. So that's that. Still get similar type of flow lines going past there. Let's look at the velocities. Very similar, but the output itself does look more refined and I think more acceptable. And as you guys can see, that is close to steady state, or basically steady state, since we don't get any changes no matter at what time we look at in that vicinity. So when we export the data, we will most likely pick a random time slot at let's say 17 hours into the analysis. Next we will be exporting the results from RAS Mapper so that we can import it eventually into Civil 3D, so that we've got inundation boundaries, perhaps the color graded flow plan, if you want to call it that, and then of course the water surface elevation with, let's say, a few contours on that as well. Just quickly show you what I mean by that. So that is, I hate that it doesn't automatically change this, that it actually works. Let's make that 1400. That might be too much, still not enough. Okay, so that's way too low. 1500, that should be okay. Okay, so we've got a pinkish band there. Let's just quickly put on Contras as well. That'll give you an idea of how the water level drops in the river as you basically go downstream. So every contour there is a meter difference in water level, and so over there it's basically at 1580, and over there it's 1576. Okay, to export this, you go to your geometry. You do not associate the terrain layers, you export layers. Nope, you manage all map layers. This brings you to this little window. At this stage we've got 3 layers already, but we want to add a new one. We said roughly at 16-17 hours. Let's make it, we know any of this is roughly okay. As you can see, this is not as in so many intervals as we specified for the computation, but it just reduces the output size of the HEC-RAS model. So 1500 hours, 1600 hours, all of them should be exactly the same. We would like the inundation boundary. Let's just go back there. Let's, for this video, let's use 1830 in all of them. That's a polygon that we want. Inundation boundary, add map. Okay, so we've got that one. Let's add another one, because we would like to see the velocity as well. So then we go to 1830. 1830, it's a raster based on the geometry. That's what we do there. That's a velocity map, adding that map. And we add another one, which is going to be the water surface elevation. That's the one we want. Once again, 1830. Just to be constant. Raster point on terrain, water surface elevation, add map. Okay, so now that we've allocated or assigned what we want to save, we actually should save it. And as you can see here, the map has not been created yet. So then compute, update. Compute, update, and then compute, update, stored maps. So now we've got those maps and they're up to date. You can also look at them if you want to over here. Okay, so that's basically the maps that we've got. There you can see the inundation boundary, and all of that we will be importing into Civil 3D in a while. One thing that I neglected to mention earlier was basically to show you where we've got too little survey area. I mentioned that we requested some more, but let me show you where. Okay, so if we look at the flow, if we turn on the 2D flow areas, you can see the actual mesh, and then everywhere where you've got the water level against the boundary of your 2D area, we can assume that the water is actually touching the boundary. So in the upstream reach there we've got too little, over there we've got too little, all along that segment right there. In this vicinity we've actually got enough. Over there I'd like to have a little bit better defined survey, and then of course this downstream portion for the entire length as well. If we look at the other side of the river, we can see that it is close to the boundary, but it is actually against that wall. We can check this by looking at the water level right there. As you can see, the water level is around about 1579.9, so let's call it 1580. And then if we look at the actual geometry depth or the terrain, over there it's 1581, which is rather significantly higher than the water level, so we can assume that the water is not overflowing onto the road. That's one neat little thing that we can check. Another thing that I didn't mention at all is these profile lines. Let's say for instance we want to see the water level as it goes down this river. You can create cross sections going down this river to show you how the water level, flow velocities and so forth looks. So basically you go to profile lines, you click on the little plus, and then you start drawing your section. At this stage it's pink on pink, so you can't really see where I'm drawing this now, but you can roughly see that thin little pink line there. Let's just draw it like that for now, just to give you an idea, and then double clicking ends it. So let's save that. Long. Press OK. Then we've got a long section. If you click on it, you can see the increments of that specific long section that I drew, and then the chainages along it as well. So now we can right click on the name, or on the man. You can right click on it and you can say plots, terrain. So that's the terrain plot. But if we turn more layers on, let's put that on, then we can plots, terrain, nope, time series plots. Let's just look, maybe it's this rather that one. Water surface elevation. So then we've got another plot with the water surface elevation and the terrain below it. Once again, along the chainage, or the station as they call it. We can also have a look at the velocity. So then we right click on it, plots, velocity. So that's how the velocity differs along that line. So the maximum velocity we got on that section was around about 3.5 meters per second. For that we can also generate tiny little cross sections. Let's just add another one. Let's say we would like a cross section from there to there, length of 151 meters, cross 1. So then we've got cross 1, plots. We would like, let's see the velocity as it changes. So on the terrain it's absolutely 0, and then it jumps up to around about 0.6, goes up, maximum of 3, down, as one could expect it over there. And that actually, if you look at it like that, it's 3, just over 3 there, so that's a little maximum we got there. So that's a neat little feature. And let's just look at the water surface elevation as well. Wow, this looks slightly exaggerated, obviously, because that's 20 meters and that's a meter. But anyway, so you can see how the terrain looks, and then the water surface elevation and how it flows over that. That's actually rather neat to see the massive difference in water level right there. All of this can obviously be exported. So we've got terrain profile. Oh man, now I'm sorting it. Station, profile, and then the terrain. So that is the water level, and that's the terrain. And then we can export it to Excel or wherever you want it to be used later. And that's it for that. So we've already saved those. We've looked at long sections. I've spoken about the 2D area not being big enough, where we need more terrain. That's a wrap. Okay, next we will have to convert all of the maps and the output data to a usable format that Civil 3D is capable of reading and understanding. The only one that actually works in this case is the inundation boundary, since it's literally just a polyline or a boundary line surrounding the results, or the actual water level. Okay, for this we will be using QGIS. So basically open up your trusty little browser if you haven't installed it yet, QGIS, search that, and you download QGIS. This is basically a free open source cross-platform desktop graphing information system application that supports viewing, editing, blah 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 blah. And whenever the website opens, we can show you. Obviously the internet is amazingly fast today and absolutely nothing is happening. Anyway, let's move on. Let's assume that you've already downloaded the installation file, installed QGIS, and you are ready to open it. You can close that, we won't be needing that anymore. Then we open QGIS desktop. I'm running version 2.18.4. I'm assuming most of them will work relatively the same, so I don't think it should be an issue. Okay, no, I don't care, let's just close that. Okay, so we don't have any recent projects, everything is brand new, so as you can see it's a clean thing. How this works is relatively straightforward. It was exported as a raster layer as we chose in RAS Mapper, so we add a raster layer. We are in the HEC-RAS example. We would like to see the that would be plan 1. There we've got the output files that RAS Mapper generated for us. We've got a water surface elevation, that, and then the inundation boundary. For now, let's import the water surface. No, that's not that nice. Let's do the water surface elevation one. So we've got water surface elevation. We open that and voila, imported. Gives you a little error there, but don't worry about that. Over here we can go and we can change the display style. The single brand, let's change this one, let's use that one. That, it's a plasma. There, apply that. Why did it disappear? I did something wrong. Obviously. Okay, let's try that again. I did something stupid, but I'll explain it to you now. So let's re-import the velocity surface. The way we change the colors of this is by double clicking on that. This brings up this. We want to use the single band pseudo color, and the plasma one sounds fine, but as you guys can see, this is empty. So basically the bands haven't been generated yet. The way you generate the bands is actually by typing in the min and the max there. So we do that, we've got colors, apply that, and that'll then update this. So then we've got that. The way we export this image is by right clicking on that, and we say save as. We want a rendered image. It's a GeoTIFF image that we want. We want to save it as. It will save it under this. This is a different project. Let's get it to the example that we're busy with. Plan. So this is the Geovelocity image. So we save that. All of this stuff will be left as is because it'll automatically scale everything, and the extents of it will be fine. So we say okay, so we've got that. Now we would like to have the contours of this. With that we go to raster, extraction, contours. Output file, we would like to do that from the velocity, not the file we just created, from the initial one. If you don't do that, the program for some reason creates 70 million contours instead of just the ones that you're looking for. So select the initial input file, the output file for contour lines vector. I'm assuming that's the file name. Let's give it a name. That would be the Geovelocity contours. And the contour interval, I think the 0.5 worked very well in this case, and we say okay. What? Failed to create it. Why? Let's try that. File type, we would like it to be that. No. What was it supposed to be again? That should be a shapefile. Geo image velocity geo. Let's make that Contras. Save. Okay. Processing complete. It worked. So it should be set as a shapefile. Yeah, assuming that. And then no, you've already done that. So now when we zoom in on this, you can see there's contours, and you can turn them on and off, and the image on and off. So there's the contours that we just created. Obviously the QGIS program has got a lot of different functions towards it. I'm not a QGIS expert, so yeah, let's just use it as it is. Okay, but this finishes our work in Quantum GIS, ready to be imported into Civil 3D. So now we can close this. Let's just minimize it for now, because we haven't exported the water surface elevation. So no, we're not done. I lied. Let's quickly bring that in. Hide this view. Details. That's what we want. We want the water surface elevation. Open. So that's what we've got there. Let's just turn all of that off. Running through all of these steps again. 1570 looks okay, and then that would be let's make that a 6. Okay, so it created our bands. We apply that. We've got bands. We want to save this as a rastered image. Geo water surface elevation image. Yes, that sounds fine. Okay, exporting has been completed. Unsupported data source. Oh man, I can't believe that. Save as that GEOTIFF. Why are you doing it there? No, this plan. We wanted elevation geo image. That's what we want. Yes, now I did it. I don't understand this thing. Anyway, raster. Extraction. Contours. Not that one. We want not the velocity, but we want the water surface elevation. The original input file. We would like to export this as a shapefile. Yes. And that would be the geo water surface elevation contours. Once again as a shapefile. Meter intervals worked nicely, and we've got contours. So now we're done in this program, so we can minimize this and then head back to Civil 3D. Now that we're back in Civil 3D, we can turn off the layers, the manning layers that we won't need. So that's done. Let's create layers that we will be putting the GEOTIFF images on. Image, water surface elevation, and another one, image, velocity. Velocity. Let's do that. That is basically done by, let's import the water surface elevation first. So that would be map insert. Map double I insert. Command. We would like to import from the correct location first of all. Desktop, example, plan 1. Then we would like we set the water surface elevation. So that's the water surface elevation image. Imported it right there. We said okay. Why is it gone? There it is. Then we can turn the background transparency on and off, and there we've got the water surface elevation color graded image. Let's go over to the velocity, turn that one off. Same command. Map insert velocity. There we've got the velocity. Once again turn that off. Now we would like the contours, so let's create other layers for the contours. Let's call it contours velocity. This time it is map import. Velocity geo contours. That's the one. And all of this is already set up, so it's as easy as that. And we've got velocity contours as polylines. You can obviously go and style those according to your liking, but as a standard, that's actually not bad. Let's add a new layer, contours. This would be the water surface elevation. Make that the active layer, turn that one off, and then we can turn off that one as well. Let's turn that one back on. Did I just put the contours on the wrong layer? Oh, cool. It already creates a specific layer for them. So let's turn that specific layer off. That's it. So now, since we've got the contour layer for this, I know it's actually not going to work, but anyway, let's insert it. So it's map map import for shapefiles, map insert for GeoTIFF files. So that's the water surface elevation contours. Once again, that's already set up, and voila, there you have it. Let's insert the inundation boundary as well. The inundation boundary, that comes straight from RAS mapper, so that this did not go through Quantum GIS. And that's already set up. It gets imported like that, so if we isolate it, we explode it, and then we are left with the inundation boundary lines. That's contours. That's actually on the wrong layer now, so let's change this to the inundation boundaries. That would be inundation boundary, that one. Cool. Unisolate. So there we've got the inundation boundary, the background image with the water surface elevation, and then the water surface elevation contours. Obviously this color grading is represented by the grading that we assigned in Quantum GIS, so you might want to include a legend of some sort and perhaps a few leaders or contour elevation markers to indicate the water surface elevation along the profile. And that's round about it. That basically sums up or summarizes how to create a surface using normal drawing input data, create a civil 3D surface, fiddle around with the way that surface is displayed, adding a bunch of break lines to it, exporting that surface for use in HEC-RAS, creating a Manning layer map. They call it a land cover layer in Civil 3D. Not Civil 3D. RAS mapper or HEC-RAS, creating that, setting up and running a 2D HEC-RAS analysis in HEC-RAS, looking at the results, sorting out some of the issues, exporting that, going about exporting all of the results that we want from that into a format that can be read either by Civil 3D, or you go over to Quantum GIS, taking that set of data, exporting it with nicely detailed color graded images, and creating contours for those results, and then of course exporting that as shapefiles and GeoTIFF images to be imported into HEC-RAS.